Okay. Okay, so we are continuing with our same paper about eternal war in memory. Uh, okay, so last time we were able to cover only some background. So we are now going to talk about the currently used protections, which we can at the time of writing of the paper, which can be deployed to protect against memory corruption attacks. So one of them is stack canaries. Keep in your mind the previous figure, which we discussed in the last lecture. Remember, we said that the first layer of that attack model is like we have to have some vulnerability in the program, right? So if there is no vulnerability, then you cannot exploit it as a first step of your attack. So this stack canary approach actually tries to protect against try to protect the first step of the attack, where you are trying to, for example, exploit the buffer overflow, so that you can move on to the second step. So how it works? So let's say have a look at this example. Let's say you have this C code. So yeah, I didn't have the time to animate it. So sorry for that. So let's say we have this C program, and now how the stack is used. I explained it last time, but let's have a more clear look on the things. So when you are executing your main program, before calling this function, vulnerable function, let's say, what will happen that the address of this next statement definitely will be translated into assembly, and then address is at the granularity of the assembly instruction, but we are just trying to relate the things. So rest of this return zero statement, it will be loaded, it will be placed on the stack or pushed on the stack. So let's say this was the top of the stack at that time. So return address is pushed here. And once it is pushed, then what happens that you start the execution of the vulnerable function. But before starting the execution of the vulnerable function, any parameters that you pass to any function, they are also placed, they are treated as the local variable of that function. So they are also placed on the stack, and then any variables within the body of the function, they are also treated as local variable, and they are also pushed on the stack. So here we are passing one pointer. So that pointer is, let's say, is also pushed on the stack, and then the buffer is also placed on the stack. And after that, whatever statements you need to execute, they are executed. Let's say it is this for this function string copy. So here what you are doing is that you are copying whatever you have the address of the string, so that string is copied into the buffer, and that string is provided by the user. Now, how the user can actually use this vulnerability and then overwrite or do the buffer overflow. So let's say the size of the buffer is 64, and here so you have location of 64 bytes, but then your user provides an input string of 128 bytes. And let's say it has a 128 character array. So what will happen? It will start filling this downward, because if, let's say, we assume that stack goes up, then it's mean that the addresses are increasing downward. So the first, whatever the first character, it will be written here, the next one here, and so on. It will keep filling the next 128 locations. So it will overwrite your input, all the local variables, and also the return address. So now once you are done with this string copy, then it's time to return from the function. So when you want to return to the function, you need to look at the return address. But that is our return. Now it is our return. So let's say the address points to a malicious code which the attacker has already injected. So now what will happen that this malicious code will start executing. Okay. So this is the problem against which the protection of stack canaries or stack cookies is used. So how it works here, that we still have the same program, but what we do is like you push on the stack the return address, but then between the stack address and any other local variables of that function from which you are going to call, you put a random value, which you name as a canary or as a cookie. So you put a random value, and then everything else works in the same way. So you have still that pointer here, you still have that buffer. And now if attacker, let's say, provides an input string of 128 characters, so still it will overwrite everything, including the random value. But the difference is that this time, once you are done with this function and you are going to return from here, before returning system checks, definitely for this one solution to work, you need the system support. It is not like only the application code is working independently to enable this protection. So system will check that, okay, the canary which was stored right above the return value, so it checks its value. If the content of this location is equal to the stored random value, then it means that there was no attack. But if it is something else, it means that your buffer overflow has happened. So as a result, you decide that, okay, I have detected an attack. So this is how canaries or cookies, you can use them to detect a buffer overflow, exploitation of a buffer overflow vulnerability. However, there are problems with this solution. No, nothing is perfect. So the one problem is that, how you have designed it. So like your criteria of where you are putting the canaries. So the criteria is like you are putting the canaries only above the return address. So which means that these return address are used only by return instruction. But if you are returning, you are making a jump in the code using some other instruction other than the return, then there will be no canary placed, and it will be not possible for the defense mechanism to detect if the canary was ever returned, because there is no canary placed in the first place. Second issue is, remember we talked about the indexing error in the last lecture, like where you can provide, a user provides the index from where to read it in an array, right? So in that, if there is a program vulnerability of that type in the user program and the victim program, you even don't need to do the full buffer overflow. You just need to provide an erroneous index, and the value will be written only at that particular erroneous location, or read from that erroneous location. Okay. So let's say if there is not shown in this program, but let's say that if there is a indexing error or indexing vulnerability in the program, so basically the indexing into the array is done based on the index provided by the user, and the attacker provides the index such that it points to the location where a return address is stored. Now, in this case, even if you are using the canaries and random value is there, but if the index provided by the victim, by the attacker is successful to write at the return address, now when returning from this function, system checks, okay, is the value stored in this equation the same as like which I stored, is it the same, equal to the stored value? It sees yes, and it thinks there is no attack, but actually there is attack. And it will, the system will allow to return to this address, and as a result, your malicious code will start executing. Okay. So then how we can protect against like this situation at this case where the canaries are broken or canaries are defeated. So the issue is like, okay, even if you have defeated the canary protection, you still need the injected code. So you still need the code to be injected so that you can execute it. So now how the code injection works, and we will then talk about what is this def, or write exclusive or write exclusive or execution protection. We talked about it briefly yesterday, but in the last lecture. So let's say we keep in mind the same program which we have seen in the previous slide. So now let's say that the input which is provided by the user is also the user or the attacker applies that input to overflow the buffer. And here I am just making a small change to make the example more easy to understand, that the size of the buffer in the program is not 64 byte. I'm saying let's say it is 4 kilobyte. Okay. size of the buffer in the victims program is not 64 bytes, that's 4, so that we can store some meaningful program in it, right? Because in 64 bytes, you cannot hold a meaningful program. Definitely, it is a prior example. So let's say that, okay, you are still using canaries. So your system placed the cookie above the return address, but then your attacker was successful because of the indexing error to override the return address. And not only that, because of like, now this time your attacker is also not even overflowing the buffer. The buffer size is 4 kilobytes, so attacker provides the 4 kilobyte input. Let's say 4 kilobyte string. And that string is, as I said last time, that the input, the string input which you give, it is basically at the end of the day translated into a binary. Now, if that binary translates corresponds to a program, you can execute it, right? So let's say that it is a meaningful program, a binary of a meaningful program. So that strings will be written here, like let's say first. Now, every instruction, depending upon what ISA you are talking about, it is possible that different instructions have different size. Like, for example, some instruction is, let's say, one instruction is 4 bytes, another instruction takes 6 bytes, another 8 bytes, depend upon the type of the instruction. But anyway, so let's say you are able to write here the bytes, 4 kilobyte of data. And because of the indexing error, you are also able to override the return address with this particular value. And let's say in this example, this particular value points to the location of the stack where you have placed the first instruction, right? So now what will happen that, okay, even if you have the cookie there, a canary there, on the return address, what will happen that you will, your code will, your next instruction that will be executed is on the top of the stack, and this program will be executed. And by executing this program, depending upon what type of instruction it is executing, you can ask it or make it do whatever you want it to do, right? So the problem here is that the attacker can inject the code into the stack through user input. And indexing error is permitting permitting the attacker to override the return address. For example, in this case, we have a particular value, and when this return address, when after executing the function, what happened is that the PC is loaded with this particular value, so the instruction will start executing from there. So this is the problem against which we need the protection, and the protection is provided by DEP or DEP, or Data Execution Prevention, or it is also known as write exclusive execution, which means like you can write something or you can execute you can write a page, memory page, or you can execute that page. You cannot do both things. A page is either writable or executable. Okay. So writable memory pages, they cannot be executed. So since we are writing in the stack, so whatever is, since it is this memory location is writable, so this protection says that you cannot load the data, you cannot load the instructions from this location. So it is not allowed to load this address into the program counter. And as a result, the attack will fail. Okay. Okay, so then attacker says, okay, fine, you don't allow me to inject the code, I can do something else. So remember that address space of a process is divided into different segments, like data segment, code segment, stack, and heap. So the data segment is used to hold your global variables. Stack is used to hold your local variables, any return addresses, or parameters stored to functions. And code, and there's the code as clear from the name, and heap, any memory which is allocated or deallocated at the runtime. Okay. So this is how normally it looks like. At the start of that, the lower side of the address, you have the code segment, and on the higher side of the address, you have the stack. So you first have code segment, then you have data segment, then heap segment, and the stack. And stack goes upward and heap goes downward. Okay, and here it's shown that addresses are increasing downward. Okay, so let's say we again have we keep everything same again. So, and now let's say our dep is activated. Like we cannot execute the code from the data pages. That is not allowed. So everything else is same. So this time what attacker can do is like, okay, you don't allow me to inject any code into the DAT. I can inject, but I cannot execute from the stack. So what I can do is that I can, let's say if there is still indexing error in the program, and using that, I can override the return address with my own known address value, such that this address value points to a known location in the code segment. So then by using that, what I can do is that I can have a starting point in the code segment of the victim address. And then for this to exactly understand, you need to know how return-oriented programming, because here the attacker is trying to use the return-oriented programming. So what you do is, as I explained it last time, but then next week we have a more clear example of that you actually try to stitch together different code snippets from the code which is already located in the code segment of the victim. So you are not injecting any new code. So the pages located in the code segment, they are only readable and they are executable. So dep doesn't protect against them. So if they are executed by the attacker, so dep will not be able to identify or detect the attack. Okay. So attacker is not injecting the code in stack this time and discovers let's say an initial gadget in existing code, for example, libc, which is like mapped into the code segment of almost all the programs which are written using the C language. And then the attacker links an initial gadget with other gadgets to construct a program that achieves attacker's target. However, the requirement for this type of attack to work is that attacker knows mapping of gadgets. For example, this particular address in our example, in the address space of the victim. So attacker knows where those gadgets are located within the address space of the victim. Okay. But if attacker doesn't know that, then it can be a problem for the attacker. So this is exactly what is like, this is exactly on what the ASLR relies. So ASLR says that, okay, so here, let me try to explain. So in ASLR, what you do is, remember, normally what we say that without ASLR, that you have on the lower side of the address space, when I say lower side, it means the lower address side. You have the data segment, code segment, data segment, heap, and then stack on the high side. So locations are fixed. Everyone like knows that, okay, what is the start of the heap address as a heap segment or data segment or code and the stack segment. Now, what does the ASLR does? It actually tries to make it harder for the attacker to find the address of the gadgets within the code segment. And to do that, what it does is that it randomizes the location where code segments, where the code segment starts, or where the data segment starts. The starting address of every segment is randomized. So if it is randomized, then it is not possible for the attacker to know that, okay, where the gadget is located. So let's like try to follow the same example. So here, see, we have like stack on the higher side, and then heap is in the middle. Here on the higher side, we have the data segment and the code segment. Now, if attacker tries to override the return address by using the indexing error with the same value, now we don't know which particular this address is pointing to what. I mean, is it pointing to pointing into maybe within the stack itself, or maybe it is pointing to code segment or data segment or heap segment. Or let's say even if we turn out to be lucky and this address is still pointing inside the code segment, maybe code segment is shifted in the address space in such a way that yes, this address still points within the code segment, but not at the required point. Okay. So there is still some overlap of the address map where address space where the code segment is mapped now and was mapped previously, but not the exact overlap. So as a result, even the address which the attacker knew about the address of the gadget, it will not be valid anymore. So what ASLR does is that it makes the location of gadgets unpredictable or unknown by randomizing the location of heap, stack, data, and code segment in address type space every time it is launched. So every time you launch a process, for example, just to verify it, or to what you can do is like, let's say if you have a variable in your program, simple C program, and you simply print its address. And every time you run the program, a different address will be printed, not the same address. Okay. So because that variable resides where, if it is a, let's say, local variable, it resides in stack. If it is a global variable, it resides in the data segment. Now, every time when you launch that program, what happens? That the starting address of the data segment or the stack segment is changed. If the starting address is changed, definitely it means that also the value of that variable located inside that segment is also changed. The address of that variable is also changed. However, if you disable ASLR, for example, on Linux, you will see that every time it will print the same address. Okay. And as a result, it will become difficult for the attacker to find location of the gadgets in the victim address space. So just to answer the question, for example, let's say even if let's say if I am an attacker and you are the victim and you are not using ASLR, how can even then I know what is the location of the libc in your address space? So libc is located in code segment. You are victim. I am the attacker. You are not using ASLR. How can I know that what is the address at which the libc is located within your code segment?
If the attacker is also not running ASLR, then they can also run the common C library and then figure out.
Yeah. So the thing is that libc will map. If you are not using ASLR, I'm not using it, libc will be mapped at the same. By looking at my location of libc, I can get your location of it. Okay. And even there are other tools, like for example, suppose that you downloaded a binary of some program from the internet, publicly available, and I also downloaded. I'm the attacker. You are running that binary. There are some commands which I can use on Linux, which will tell me that, okay, what is the reference table which tells whether at what particular location a particular function is mapped. So if ASLR is not enabled, I will know that if you run the same binary, that binary is mapped at that particular location in your address space. Okay, no questions. Why? Yes.
I think you did answer it, but you're saying that with ASLR, even if the attacker knows the return address, if it does that exploit, it won't work because it's not going to matter. It's not going to link to the same libc.
Yeah, it doesn't point to the same
It
location.
doesn't point.
So then question is that, okay, how can we, as an attacker, how can we bypass ASLR? I never did it, but this is what the paper says. So what you can do is like, you can use the information leakage as a tool to bypass the ASLR. Now, how the information leakage works, let's say we again have this, everything is same, okay? So for example, what you can do is, let's say you have a buffer overflow vulnerability in your program. So which basically means that you give an input and the programmer never put a check in the program that the size of the input must be within the range. Okay. So what you can do is you can exploit the buffer overflow to write a pointer located in stack that is later read and then printed by the victim process. So let me explain. So let's say again, this is your stack. I'm not drawing everything, but let's say this is the buffer. Here your buffer is located into which the value which is read from the user is placed. Okay. And in the buffer, there is some pointer, local pointer of the function. Okay, let's say I'm naming it as read pointer. So what the program does is that, let's say it first reads the value from the input, places it in the buffer, and then it, let's say, uses this read pointer, which actually points to some memory location, to read the value from that location and print it. So like it is like printf. And then you dereference this read pointer. Okay. So now let's say I do the buffer overflow and I'm able to overwrite it with some other address. Okay. And if I overwrite and let's say I'm naming it as malicious address. Okay. So now I don't know. I don't know exactly where this malicious address points because ASLR is enabled. But I'm just trying to, like, let's say, hit and try. Okay. I do malicious address, put here malicious address, and then it says printf. So whatever is written at this malicious address in the memory will be printed, right? Now, let's assume that whatever it prints is something like key A 0F 0C something D. Okay. And it turns out that when I look at this number or this string which is printed, and when I look it at and I translate it, it looks out that it is equal to the binary of call printf. Right? So, which is basically what happened is, so it is telling me that the malicious address with which I did the buffer overflow, I was able to read some code, and then that code actually points to the call printf, and this call printf is located in libc somewhere. Let's say here. No, sorry. Call printf is located in your program. And then when you do call printf, it starts executing printf, which is located, which has its code in the libc. Okay. So if somehow I'm able to read this address by this code by providing the malicious address. So again, I just turned out to be lucky. So, and using that malicious address, I find out that I get this particular code, whatever it is, assembly code. Now I know that, okay, the address I provided corresponds to this point. And now everyone knows what is the layout of the libc. It is public information. So if it is a public information, then I know that, okay, this is the offset from the start of the libc. And after this offset, the definition of printf is available in the libc. Okay. So if I know this address, and I also know this offset, what is the amount of offset, I can get this starting address, right? So if I can get this starting address, I can do ROP, return oriented program. But then it is not easy. Okay. So the next thing they discuss in the paper is about what are the false positive and negatives of the detection attacks. Sorry, while you are detecting attack or while you are protecting against the attack. So false positive basically mean that when your protection mechanism reports you that it has detected an attack, while actually there was no attack in progress. So it was like giving you false information, but in the sense that it says that there is an attack, but actually there is not. False negative is opposite of the same thing, where your detection mechanism says that it reports you there is no attack, but actually there was an attack in progress or it was already launched. Okay. So we don't want, we want our detection mechanisms to have ideally 0 false negative and 0 false positive. Why? Because they are not good for both from the performance perspective and from the security perspective. So why they are not good? So let's have a look. Let's say you have two detection, two security mechanisms or policies, A and B. Let's first look at this one. On x-axis, we have the policies, and on the y-axis, we have the detection rate. Detection rate is like out of total number of launched attacks, how many number of attacks your policy was able to detect. So let's say if our policy A has 95%. So it says that I was able to detect 95% of the attacks. But then out of those 95%, how many were the false positive? Like the policy said that yes, there is an attack in progress, but actually there was no attack. Okay. So why should we, when we are analyzing our results of like, let's say evaluating any mechanism, we are analyzing the results, why we need to be careful about false positives? Because the issue with the false positive is like, let's say you have detected an attack. So what to do after that? You must have some kind of mechanism to stop the progress of that attack, or if it has already succeeded, to take some corrective measure, right? So which basically mean you are doing something extra which increases the performance of our head. Okay. Now, if let's say in this example, it says that detection rate was 95%, but actually actual was 70%, and remaining 25% was like false positive. So it's mean that for those 25% of the time, of the cases, you are stopping your system, you are doing some corrective step, or you are like doing whatever you are supposed to do after detecting that. Okay. So which will cause you performance overhead. So they are bad for the performance. And then let's say have a look at the policy B here. Let's say that it has 60%, no, sorry, let's say it has 40% detection rate, right? But which basically means that it says that I was able to detect 40% of the attacks. And but actually there was like 20% false negative. So 20% for the 20% of the attacks which happened, your policy was not able to detect them, assuming that there was actually an attack while it assumed that there is no attack. Okay, it reported that there is no attack. Now there are two cases. One, there is actually no attack and you reported that there is no attack. And one, there is actually an attack in progress and you reported that there is no attack. So this is like false negative. And they are, if you are like looking at things from the security perspective, they are more dangerous. False positives are also dangerous, but these are more harmful for security, because you are first thing is like you are not able to even detect. If you are not able to detect, you will not take any countermeasures. Okay. So it will lower the security. So the issue with the high false positive, so we don't want high false positive because it degrades the performance, and we also don't want high false negative because it degrades the security.
One question. For policy A, is the 95% including the false positives, or is 5% of that false positive?
Yeah, no, including the false positive, because I'm just reporting here, let's say, whatever is detected by our system.
Okay.
Yeah.
Assuming 0%.
So, so here, so what we are actually saying is that when we are, let's say, you design some mechanism and then you are evaluating it, so in your evaluation, you should exclude false positive, and you should exclude false negatives. Okay, so that your results are, clean results. Yes.
Assuming 0% of false positive and false negative is not achievable, what will be a desirable and achievable balance between those two percentage?
So let's say it again.
So if 0% false positive and false negative is not
1%?
possible,
1%?
0%,
0%.
yeah. So what will be a balance between those two that we want to achieve and that is actually possible? Should we go for a 0% of false positives or 0% of false negative, or a,
You are saying that it is not possible to achieve 0% for both of them.
yeah,
And there is a trade-off, like, let's say, you can achieve, if you try to reduce the number of false positive, it results in increasing number of false negatives, right? Okay. Question is clear? Anyone want one? The question is like, it is not possible for us, like our ideal, we want to achieve is to have 0% false negative and 0% false positive. But let's say we are in a situation where we cannot do that. And the situation is like, if we try to reduce the false positive, it results in increasing the false negatives. And if we try to reduce the false negative, it results in increasing the false positive. So there is trade-off. So which one should we prefer? Lower number of false negatives or lower number of false positive, and why?
It's a lower number of false negatives, because like you were saying, if the system fails to detect any attack at all, then we have no countermeasure, no recourse to correct that. As to where if it detects a false positive, it might require more performance overhead to mitigate the false detection, but at least you're still having some sort of countermeasure. You're being more precautious than, on the other hand, just letting something completely attack your system without you doing anything.
Yeah, it actually depends on like how you are looking at the things. It's like, if like, let's say you are designing a system which is, it is like critical, let's say if you miss at detecting an attack and it can result in some fatal consequences, like let's say it can take life of someone. So you don't want to have even a single false negative, right? But let's say you are designing a mechanism that works on detecting denial of service attack. So denial of service attacks, they are like, yes, they reduce the performance and degrade the performance of the system, but let's say they don't result in like death of anyone. Okay, so maybe you can tolerate there in that situation relatively some reasonable number of false negatives. And also another thing is like, yes, false, let's say you have a system which has 0 false negative, but as we are keeping our assumption, but it results in a higher number of false positive, which makes our system super slow. So that is also a like aspect to look at.
I've seen that some of the papers that we have read, the authors or the researchers prefer solutions that have better performance or less overhead over more security. So would you say that it's better to have better performance than security, or?
Again, I mean, there is no security without performance overhead. You cannot say like, I designed this security mechanism which incurs 0% overhead. There will be like, even we like the catalyst splitter, right? They said less than 1%, but it's not 0, right? So ideally we want, and here also in this paper, they are again, they are raising this point that yes, there are some security protections which work, but their security overhead is so high that they cannot be deployed in real life. They can maybe, like, you can use them to publish a paper, but not to. So it depends, like, what is your requirement? How much performance degradation you are ready to accept. Okay. And it again, how much you are ready to accept depends upon, like, for example, if it is a real-time system where you don't want to miss any deadline of any task. So if you devise a security mechanism which yes, give you security, but then it results in some tasks missing their deadline. So maybe you will say, no, I don't want this mechanism then. Because it is meeting my deadline is my prime requirement.
So is there a way, like, ignoring the overhead and the loss of like functionality of some devices that they can like completely avoid these kinds of attacks? So even if it takes like 100 times overhead or whatever all stuff, do they have ways?
Would you like to use such a system which can completely avoid the attacks, but then?
Well, no, but I'm wondering if they have some sort of solution that they come up with for that, or if they just haven't even bothered to.
Yeah, I don't know, I mean, if there are some solution like that, but even if they are available, no one will use them. It makes me remind of a very funny thing. I was in Turkey, I was in Turkey and I had a like friend, he was like also doing PhD there. And he was working in some defense company of Pakistan, but he was like on student of study visa. What was it? What is the Arrow? There is a space Sparko, Space Agency of Pakistan. So he was working there and he was like, whenever we need to access the system, so he needed remotely, he needed access. And he asked them over the email, can you please enable it? And they were like, because of security issue, we have disconnected it from the internet. So you have a secure system, which is only locally working, but you cannot access, you cannot like use it. Yeah, so you have complete security, zero performance. Okay, so any questions?
That's one thing I was going through when I was reading. And I was like, if there was a way to make it so that there could not be any invalid memory rights, would they even need to worry?
Invalid what?
Invalid like rights to memory?
Okay.
Would there need to be any sort of worry about having like invalid read of memory? Because then you could like maybe take some of the cost that you're doing on preventing people from reading the memory and allocate that and just completely preventing any rights. So even if they can read it, if they can't do anything with that information, you need to worry about protecting them from seeing it or not.
Is it only me who is struggling? Maybe
I think I might be struggling
there's something,
with that myself
something
too.
wrong in my listening powers.
So yeah, if you can make it so there's no invalid memory rights, like at all allowed, like there's just
Okay.
completely, you cannot, no one can invalidly write to memory. Do you need to worry about anyone reading the memory at all?
Yes.
Yeah, so.
Yes, because let's say I cannot write to a memory location for which I don't have permission. But I don't have permission for a memory location, but I can read from it. This is what you're asking.
Yeah,
So are you saying like, as a victim, do you need to worry about that or not?
Mhm.
What is the obvious answer?
Yes.
Why?
Yeah, so my thing is, if they can't do anything with that memory access, why does it worry that? Why do they need to read it?
Let's say the memory location that I can access. In that memory location, you have stored your credit card password.
Oh. Yeah.
Okay.
Well, then you'll still have the data leakage issues too.
So I was thinking more of if they could read like the actual memory address with that. They can't write to that address. So I mean, mostly, I guess, focused on what is it, return-oriented programming, where if you can't get them to like, if they cannot write again into the,
Yeah, so in return-oriented programming, you don't need to write. You like, this will actually answer your question. If you are talking in terms of like, okay, without writing, can I launch the attack? So yes, without writing into the memory, you can launch the attack, and ROP is an example. So I mean, as I said, I promise next week, I will give you a clear example on that. You don't need to write anything to execute a malicious code.
Remember the writer execute he was talking about? So there's a writer execute, but it prevents like executing writing, right? That's like the whole idea, obvious. But the area of like Rob is it doesn't, it's just using the existing code. So as long as it's flagged to be executable, you might not be able to overwrite it, but you can still execute that function and tell it to do whatever. So if you can you can find the existing functions that you can chain together to do whatever your malicious task is, then you've got something. If you could do that.
So actually the thing is like, as I explained last time, by ordering the instructions in a different way, you can make this new arrangement of instruction to do a new thing, right? So very like, my favorite example is a garbage and multiply. So let's say in your libc or any code which is in your like code segment, you have this add instruction. And as an attacker, I want to do multiply. So previously, maybe I need to inject the multiply code, but I cannot inject. So if this is add in the code section of the victim, and then I can say, okay, somehow, and here, so there is a jump statement, and let's say there is, you know how label works in assembly, right? They are later translated into definitely into address, but to make it easy, I'm just using label. Okay, label one, and I say jump label one. And here there was like something like add in R1, R2, and some immediate number. And I know the address of this one, 0x F30 something. And here, this was the return address of a function stored here, and by using buffer overflow, I said 0x F30A. Okay. Now what we will do is start do the addition, and then jump back and do the addition. So it will turn into a multiplication. I don't need to inject the code for multiplication in the buffer, right, on the side. But then again, I need to first discover those gadgets in the code section. So this is like, let's say an example of a gadget. So what I can do is I can stitch multiple gadgets together to make a longer program. Okay. Okay, so who is discussion lead today?
I sent you,
Okay.
Email to
Okay, you have last 15 minutes. You want me to record you or not?
Oh, I sent you an email with the.
No, you want me to record you or? Okay. Okay.
You're gonna notice, I think you guys will recognize the template I used.
So I think recording is in progress, right? Yeah, okay.
Yeah. I don't have another template right now, so it's a long. So this is going to end up being a review of what we learned about 5 minutes ago. So I guess we'll start, there's the W or the depth, right? Read, write, execute, right? So that one, I mean, we kind of covered this. It's very simple. It's the idea, okay, we have a page, virtual memory, not physical memory. With the virtual memory side, we can write to, or it can be executed on, not in between. So what he was talking about earlier, right, can only, even if we could write something and overwrite that memory location, if it's executed, if that program is there, however you implement
write or execute, whether that be on your own program or the operating system or the kernel or whatever it is, hardware even. He won't be able to write that code and then it be executed because the program's going to flag it as invalid. Same with the writable states, right? So ASLR we covered, and then you know what? Here I can just ask one of you to explain this one. It's a review. So one of you who haven't done a question, want to answer what ASLR is?
Basically just randomizes any memory pointers or memory within the code.
Yeah, so it's code and data. So it does
Yeah.
code and data. It's both, right? It's not just one or the other. But yeah, it's security and obscurity because we're just hiding stuff everywhere in memory, so it's harder to find. But of course, if you find the pointer to something, you can start kind of dissecting what it is, and that was kind of the security issue with ASLR being involved in what did he say? The leakage of information, right? SSP stack smashing. I guess I was kind of keeping this one for the next lecture, I believe, right? I think that one shows up in like section 8. But they talk a little bit about more of the canary stuff that he was talking about earlier. And then there's these 2 random ones for Windows. They basically just mention those words. They talked very little about them. A little bit, and then there's ROP, which we talked about. But then there's the exploit techniques, and I had some notes here. I'm trying to go really quick because we don't have much time. Was stack smashing, right? So just kind of overloading stuff. We've looked at this, and I don't really want to cover too much of the exploits because these were all from section 2, and I'm trying to only focus on section 2 or 3 and 4. But the idea was that it won't protect against ROP, the stack smashing protection, but it does protect against normal stack smashing, just overloading these and putting stuff where it shouldn't go, basically, right?
Okay, here is a
Yeah,
question.
yeah.
Can you use ROP without stack smashing?
Yeah, you don't need it, right?
How?
As long as you can find where those functions are, you don't need to overload anything. So if you have a memory location,
But if you know, okay, you know where those functions or gadgets are, but you don't know how to go to the first function. If you are not able to change the control flow such that it starts executing at the first function, then ROP will fail, right?
right?
And if you don't have stack smashing, what other mechanism you can then use to make the control flow divert to the first point, first gadget?
What would be the mechanism to make that happen?
Yes.
Because I don't think you wouldn't need it for ROP to work, but to find the way to execute ROP, yeah, you'd have to find some other way or knowledge to discover where these pointers would lie. So you can have it, yeah, like you said, flip that script. I'm not sure how you would do that.
I mean, stack smashing is like buffer flow is like only one mechanism through which you can, stack smashing is any mechanism through which you can smash the stack. You can override the stack, right?
Leakage.
To corrupt it. Buffer overflow is one option, right? Another is like indexing error.
Heap corruption, function pointer, I got vtable corruption.
Yeah.
Also, yeah, a lot of
So if there is any kind of approach which enables you to smash the stack such that you can overwrite a return address, then you can make it point to this first gadget you know.
So that was the section 2 stuff, but so back to section 3. Not sure how to use a MacBook, apparently. So there's probabilistic and deterministic. Those is a huge section on section on the 4th section. It was basically, this was kind of one of the huge bullet points that they had. And so the difference is that there's probabilistic, which is kind of more focused on like ASLR. So ASLR is the big kind of the main reference point. It's just making things random and kind of randomizing areas, the obscurity aspect of the security. The goal being, right, we're just making it harder for attackers. We're not really focusing on the technical side. It's just making it more difficult, because our other options are going to be deterministic, where we're actually going to create kind of like group policies, right, on Windows, more individual specific rules that outline what these do.
Okay, yeah, I have a question
Yeah.
for everyone. So I gave you like a brief idea of how ASLR works, right? You randomize the locations where you are, where your data segment, code segment, everything is there, right? Now, what is the downside of that in terms of performance? Assume you have a program. Let's say you have two processes and you have a single code. You have two processes, they are interleaved for execution on a single code. And every time you launch a process, you have to randomize its mapping of its code segment, data segment. So how it will affect the performance?
Degrade the performance overhead, right?
Sorry,
It would degrade the performance overhead,
degrade or it will increase the performance of it?
decrease, sorry, onward.
So-
Decrease the performance overhead because it has to run it every time that the program runs the memory. It has to change it every single time.
It'll be increasing.
So it is
Increasing, sorry,
increasing
increasing
the
the
overhead.
overhead, yes.
But how and why? That is kind of obvious, but how?
My intuition tells me that now you're limiting the size of stack and heap if you randomize it. Because before you would have heap and stack this way so that they had enough room to grow. But you randomize it and so you have code, stack, and data. Well, now stack is limited by how much room it has to grow.
Not really, because every time, doesn't matter when you, how many times you launch it, every time the code segment is fixed. Data segment is fixed, because data segment contains global variable, and code segment contains the code which is fixed. And then the remaining is like, you can divide it between stack and heap.
Yeah, but I was thinking, since those are fixed, and you don't, and stack isn't fixed, and you have to place stack between code and data, how much room do you allocate for stack when you're placing?
Yeah, as long as your data and code segment, think like this. Your data segment and code segment are always fixed, right? So if they are always fixed, doesn't matter where you place them, they will always take same amount of space, right? So remaining space is available. Now, are you saying that if I put the data segment above and then stack segment is here, then it can go into the data segment?
Yeah.
Yeah, but. Yes, but. It will not, it will maybe limit that how, okay, where you can map them, like arrangement, but not on the size. You can always figure out a solution where like, okay, I am doing this arrangement of the placement, but still I allow for the growth of the set.
Have we talked about DSR yet?
What?
Have we talked about DSR yet?
About what?
DSR, the data randomization?
No.
Or data speed?
No. But then let's first stick to this question. Yes.
I think because the data is gonna be randomized, it's gonna increase the performance overhead because now, since it's randomized, there's not gonna be a good ability of sharing data between whatever programs you have open, so there's gonna be a overhead between them for that, to try to get shared data. Or we're gonna be shared enough.
Okay, let me try to give you an example. Do you know that files can be, you know it, right? It's not that, I'm telling you that files can be mapped into the address space of a process, right? You can open a file and then you say, okay, map that file into the space of a process, right? And then you can do unmap, right? So if you are doing, let's say, this is where are files mapped into the heap segment, okay? So if you want to map a file and you say mmap, and if every time you map it, it maps into the same location, then it's mean it's deterministic. Now, if you want to randomize it, right, then you have to every time, let's say first time it was mapped in this region. Then next time it is mapped here. Then next time maybe, I'm just trying to show, it covers different region, okay? But every time you map, let's say you are also, your, how you access that, map file using page table, right? So if let's say you first time you mapped it, and after mapping, your page table is populated. Populated mean like you have like now entries that, okay, these are the virtual addresses which correspond to that file, and then these go to translate to these physical addresses, right? Now let's say after mapping first time you unmap it, and you map it again, and as a result of ASLR, it is now mapped after a different location. Now these virtual addresses are not valid anymore. But programmer should not need to worry about it. If the programmer should not be worried about that, then it means we are placing the burden on the operating system that the addresses which were previously used by the application to address that map should still be valid. But now let's say our file was mapped in a different location. So what you need to do is that you need to translate these virtual addresses into new virtual addresses in a way which is transparent to the user, to the application, to the programmer, which basically means that every time your file is mapped into a new location, you have an address translation from old virtual addresses to new virtual addresses. So this incurs extra performance overhead because these page table entries are now invalid, and you have to populate new page table entries, and also need to keep the translation table where maybe the programmer is still using these older addresses now, but they should point here. Okay. So as a result, that's why this is one reason why your ASL, I will come to your question. ASLR is that's why applied normally at a coarse granularity. Like they randomize the location where the starting point of the heap, or the starting point of the data segment, a starting point of the code segment, but they don't like, if you go to the final granularity, let's say every 4 kilobyte of heap is randomized. So it will incur much more performance overhead as compared to, because if only the whole heap segment is randomized, only starting addresses change, you can still use the relative addresses. Because if your addresses are relative, like it is from start of the heap plus this offset. If start is changed, doesn't matter, your address still valid, right? But if you go to the final granularity, you need more and more address transmission. You have a question?
Yeah, do you need a different, like a translation table or an offset table that keeps track of the positions and offsets of the table to translate the new page table?
Yes, you have to, because every time now you will have to have an extra table, and every time you have to update it.
And then you need to link
Otherwise,
that
your
table.
addresses used by your program will not be valid after that.
So in other words, ASLR has a performance increase at the start of a program and whenever memory is getting allocated. Right, okay. So ASLR has the downside of information leaks and it can get brute forced. Anyway, deterministic sides. So this is on rule sets, right? And it talks about CFI, and that comes up way later in the paper, but the control flow integrity and other things.
What is SSP?
SSP? Back here to your stack smashing protection. Yeah, so that was like your canary stuff that you were talking about on Tuesday. But by putting the canary and then having to check the ID and seeing if those are those match, and that's done either by the program itself or sometimes OS. I think it was saying something about a Linux distro was doing that, but not all of them, because it had some crazy performance increases, like 100% or something. So probabilistics about scrambling stuff, deterministics not so much, yes.
So that 100% thing you are talking about, what is that?
It was another implementation. So one of the issues they were mentioning was that whenever they had a system like that, they needed to expand the memory space. And so they had to, it was about 100% increase. And one of the things that came up later, actually, we can kind of jump over here, on this slide was they had, or, is that the right one? One of the problems they were mentioning is about, they needed to have about a 5 to 10% performance overhead before anything would get widely adopted. If it was anything more than that, developers wouldn't really want that architecture to get added in.
Yeah, that 100% performance overhead they are talking about is, I guess, what is this? Tainting, data tainting,
See, yeah, here it is.
data tainting, right?
Yes.
What is that, you know?
I think what you're talking about is you're putting the extra memory of, so whenever, I don't think you have that anymore. We're talking about the canaries and the user IDs, or I'm gonna call them user IDs, but the random garbage we're throwing in the front of return addresses, right? So we were adding that, so whenever our program was looking and running through this execution, and it saw that the ID of the return address in that function has changed, that program can now say, okay, that ID's changed, my return function is broken. I'm not going to execute this because something happened to it. I don't know what it is, but I'm just going to flag as a problem and then I'm going to go on with whatever else I was doing or throw an error or whatever. But one of the issues they were talking about was one of the solutions they came up with and had a big old performance impact of about 100%. And that was also talking about some of the other issues with over-indexing. There's a for loop that they're referring to, how for loops kind of always go out of bounds by one. They call one more index at the end. So you have an index of 10. Well, they always kind of go to the 11th and they call something else. So what one of the developers did was they just added 8 bytes to the end of every memory type, basically, and it added a 12 times performance overhead. But
Direct
yeah.
the question to everyone. What is data tainting? It is mentioned in the paper, and we were supposed to focus only on 2 sections, section 3 and section 4. So
The security implementation, they were. Is it where they just check, if like when the user wants to do something, if it's valid to do, or like a level of permission?
okay, so the basic idea of data tainting is this, like, what is wrong with buffer overflow, or what is the basic root cause of the buffer overflow? We are trusting something which is coming from the outside world, right? Outside world is like user is giving input. Now, the data which flows into the system is not only through your user console input. It can be in many different shapes, like you are reading data from into the program from maybe files, from user input, from the internet, right? From all those sources. So the idea of data tainting is, what you do is that any data which enters into your program or into your system from the external sources, you mark it. And then you start tracking the flow of that data during the execution of the program. And if it turns out that this data is modifying the code section, is to what the external input which you have already marked is trying to modify the code section, or it is trying to override, for example, the return address in the stack. So since you have marked it, so now you know that it should not be allowed to override the return address, or it should not be allowed to modify any code section. And then you can, if it happens, you can flag it as a detection of an attack. And this is very expensive because you need to track every data, external data, which enters into the system, and it becomes expensive as a result, and has 100% overhead. So you cannot deploy it in this.
Right, so you're talking about the control flow integrity stuff they're talking about in way later on the paper, right? That was cool.
I don't know whether they discuss it later or not, but
They have a whole almost page, I think, on it, on like
Oh, yeah.
section 7 or 8. Yes. Yes. I don't entirely know exactly where I was. Um, but I think I covered deterministics quite well. There was, so I guess I'll look through some of my notes here. There was a lot of more implementation of deterministics is harder. Typically, it seems from everyone that they were kind of writing. Writer execute was, it was alluded to that it used to be a software implementation and became a hardware implementation over time. Because it doesn't, it's more of a concept, right? All of these are more concepts, not necessarily direct ways of implementing something. You can kind of change them up, is kind of my understanding there. And then there was some ROP issues as well. And that we're using some tricks. I'm not going to cover this entirely. We don't have, how much time do we have? None. We're out. Yeah, there was just some performance overhead, memory overhead. So like issues with shadow tables. We talked a lot about performance, but there's also the memory issue too. There's a lot more cost with memory. Like if we have to store a big old table about all of the changes we've made that we might have to reference later, like that might be, it's still also a problem, but yeah, I guess, is there any other little things I can cover on compatibility between devices? We want our security implementations to be as easy to access as possible. We don't want it to be difficult for anything in the future. That was a big portion on the last like 3 paragraphs of section 4. So if you're like curious about like those details, it's very simple. It's only like 3 paragraphs that you can quickly glance over, and it'll give you a very brief synopsis of what they want you to do. But there's kind of a description in the paper of, if you're going to make a security implementation, it should follow these kind of guidelines and compatibility with existing stuff.
Okay, let's have this last question and then let's stop. So for everyone, so they have mentioned somewhere shadow stack. What's that? How it works?
So I saw shadow tables, but the table from what I was reading couldn't tell you how it works. But I could tell you that from what my understanding is, the idea is that it is it's just it's an area where we're storing, or I guess there's a shadows file on like Linux, right? Just a list of things that aren't going to be stored necessarily in memory, but we're using as a reference for other areas of active memory that's kind of supposed to be hidden, right? And it's a key place that we're storing references to existing information. That makes sense.
Yeah, but why we need that shadow? I got it, like, okay, we clear from the name, we have a second copy of, let's say, some entity, table, for example. But then what is the purpose of having that second copy in context of security?
Like a checksum, comparing the table with the actual one and check if it would change.
So this is also what is the motivation behind shadow stack. So you create a shadow of the actual stack. So now even if like attacker can override the actual stack and corrupt a return address, so you can now go and compare with the return address you have in the shadow stack. If the two doesn't match, this means there is a buffer overflow happening, or your stack has been smashed. And if they match, then you're fine. So it's just like checksum. Let's stop here. Has everyone submitted the last participation form?
Is this still a rolling issue?
I think I should put a rule that no answers in the notice in last 2 minutes will be entered. Okay. You can ask, it's okay. Yeah. What was your question?
Is this still a relevant issue in modern? Like this memory corruption?
You mean, what memory corruption? These memory vulnerabilities?
Yeah.
Yes, they are, because if you have taken programming language courses, right?
Yeah.
So I can bet if you go and if you check your code, and if you are in some program you are taking input, there is 95% chance that you haven't checked the bounds of that.
Because it kind of reminds me of how SQL injection works. Because I know how people defend against it is by using an argument. But they check the arguments that they pass in to SQL. And they make sure that you only pass.
For example, very common example is like when you write the main function, you give an input to it. And let's say you have like, okay, these are the input control parameters for the main function. And if they are like, let's say less than 4, then say, okay, print the usage function, like usage help, how to use it, right? But there is no such thing like normally, okay, if they are more than 10, then don't take some again, right? So let's say I'm calling a main function and I can pass it and like more than 4, or more than whatever the limit is. So it's mean if it accepts, it's mean it is the whatever I give as the input, it is written on the stack. So by giving a large input, I can output the stack. Who is next? I want more comprehensive in-depth presentation for you. Okay. So like, in the 2 sections you are responsible, or let me check the paper. So. So 3 probabilistic methods and memory safety. Yeah, try to cover rest of the paper.
Okay, so
Okay.
basically.
From 5 to
5 and
onward.
above.
Yeah,
Okay.
5 to onwards. Okay.
Got it.